These are your notes for today. These notes are going to be from section 1.4 to start with. Whoops, sorry. Section 1.4 to start with. And we definitely want to get today's date on there, so we remember that. Can look back at that later. Okay? Section 1.4 has to do with complex numbers. Now, I know that you've heard about complex numbers before because I taught you about complex numbers, but I'm reminding you now. Okay? What makes something a complex number?
They're letters.
The imaginary number.
Yep. What part is this? That's the real part. What's this part?
Fake friends.
This is the imaginary part. Okay? What makes it the imaginary part?
I.
It has the I in it.
The number
Okay? So we need to talk about the number I for a second. Do you remember what I means?
Isn't it something that when squared equals a negative number?
The square root of -1. That's right. Okay? If we know that I equals the square root of -1, then what does I squared equal? -1. Because if I multiply this by itself, don't I just get what's inside? Which is -1. What's I to the third? Isn't it this times this? To get I to the third, wouldn't I multiply I squared and I? So I would either get negative square root of -1, or I would get negative I. Okay with that?
Yes.
What about I to the fourth?
Would it be positive I? I mean positive 1.
Positive 1. Because I can multiply I squared times I squared to get me I to the fourth, right? -1 times -1 is positive 1. Do you remember what happens after that?
No.
Let's think about it for a second. I to the fifth would be the same as I to the fourth times I, right?
Yeah.
Which would be I. 1 times I. What about I to the sixth? -1. What about I to the seventh? Negative I. What about I to the eighth? It would be 1. So it's a pattern, right? Starts here. I to the fifth repeats the pattern. I to the ninth repeats the pattern, and so on. Okay? Do you remember that?
Yes.
There's certain different things that we need to be able to do with complex numbers. Certain operations we need to be able to do. Okay? For instance, we need to be able to say 8 plus 2i plus 5 minus 6i. Can we add two complex numbers together? How do we go about doing that? Guys, can I combine real and imaginary?
No.
The only time that worked was when? Space Jam. Right? That's the only time. Well, some people say Who Framed Roger Rabbit, but I don't think you guys know that movie. You like that? Okay. Space Jam for sure, though, right? That's when real and imaginary work together. But none of that's math. Okay? We can't combine real and imaginary. What can we combine? Yeah, real and real to give me 13. Imaginary and imaginary to give me what? -4i, right? My favorite one. Wait, do you remember why that's my favorite one? That was my nickname growing up.
4.
Yeah, it's so funny. What other operations should we be able to do with complex numbers then?
Multiplication?
We can. Can we wait for that one for just a second?
Sure can.
Which one did we skip over?
Subtraction.
So we should be able to do 4 plus 2i minus 6 minus 3i. Once again, can we subtract real and imaginary parts? No, only real and real. 4 minus 6. -2, thank you. And imaginary, 2i minus -3i.
5i.
Plus 5i, right? You got that okay? Then, for sure, we can multiply, right? So, we should be able to start at a place like this with just a scalar. Just a real number multiplier. It's called a scalar. I don't know why. It's a weird word. Okay? But here comes the problem. What should I do with this 2?
Distribute.
Well, it seems like I should do that, right? That's not a problem. That gets me 6. Are we allowed to multiply real and imaginary? Yeah, we sure are.
Boom.
Okay? We sure are. Think about this. What if we were talking about x's? What if this said 3 plus 6x? Could we multiply 2 times 6x?
Yeah.
Even though they're not like terms, one has an x and one doesn't? It's kind of the same rule here. Okay? We're just distributing this. We're doubling the real part and we're doubling the imaginary part. We can do that, can't we? Okay. So here would be our answer for that problem, 6 plus 12i. We should also be able to do something like complex number times complex number. Right? Right. Okay. What kind of mathematical property are we going to use here?
Foil.
So like this, no, foil's not a mathematical property. It's what they tell you in junior high so you don't forget it. Thank you. Distributive property. Here and here, which is 8. Here and here, which is negative 10i. Here and here, which is plus 12i. And here and here, negative 15i squared. Absolutely. Okay. Well, what can I do from here? I should be able to add my like terms, right? My imaginary terms, right? So that should give me 8. Close. Can it be plus 2i?
Sure can.
Okay. And then I've got this weird 15i squared going on. But something should remind me about what I know about I squared. It's negative 1, right? I don't want to leave an I squared if I have a choice, and I do. Okay? This is not really I squared anymore. It's really times a negative 1. So this is really 8 minus a negative 15. So 8 plus 15, which is 23. You got that okay? Lest you forget, I don't know why I said it like that. That was weird. We can say 2 plus 3i times 4 minus 5i and get 23. Why is it so dark? Lest you forgot. 23 plus 2i. I can do that all on my calculator. But you guys know how I feel about calculators, right? We talk about the math first, then I show you, remind you in the calculator. Still the same now. Okay? Any questions about this? This section also asks you to be able to do things with square roots. It also asks you to do things like this. The square root of negative 16. Can I remind you how to do problems like this? Some of you might remember off the top of your head, and that's good until we get to the next part. So let's go slow through this one. We know we can break apart numbers inside the square root, and I know I can break it apart like that. Why did I choose to break it apart like this? Do I know the square root of negative 1? Yes. Do I know the square root of 16? Yes. Because of properties of radicals, ugh, dang it. I know I can rewrite it like this. What is the square root of negative 1? I. What is the square root of 16? 4. Done. The difference, well, we'll talk about the difference in a second. What about if it's the square root of negative 25?
Same thing.
Same thing. If I do it slowly, I can do this, and I can do this, which means my answer is 5i. Now, do I have to do it slowly?
No.
No, I can say the square root of negative 36 is what?
6i.
6i, because I can do that in my head. The problem comes when this is what they ask you to do.
Ooh.
Then it's really good to know this process right here, because when I break this apart, I get a negative 1 and 16 and 2. If you talk in a college class like that, the professor asks you to leave and you're not welcome back. Same is true here. Do you know the square root of negative 1? I. Do you know the square root of 16? 4. Do you know the square root of 2? I don't either. You okay with that? So the difference comes when you're asked to solve a problem like this. How do you go about solving this problem? X squared equals negative 16. We want to take the square root of both sides, don't we? Square root here, square root here. What is the square root of x squared? I know that you all remember the fundamental theorem of algebra, which says whatever the highest exponent is, that's the number of solutions you ought to have, right? How many solutions should I have to this? So what are my solutions? I know it's got to have something to do with 4i because I did that over here, right? But here's the difference. Who put this radical sign in the problem?
It was already in
It was
there.
already there. Who put this radical sign in the problem? So what do we have to remember to write? Plus or minus. And those are my two solutions. Okay, do you see the difference?
Yes.
The last thing you're going to have to know how to do in this particular unit is something that when I taught you last year, you freaked out a little bit. I remember you freaking out. When we talked about complex conjugates. And then after we talked for a couple minutes, you were like, this is not even hard. Like, well, I try to tell you that, but you don't believe me. Because what I said is, here is a complex number. What is its complex conjugate? Well, the real part stays the same. The imaginary part is opposite. Here's a complex number. What's its complex conjugate?
Okay. 4 minus 6i.
4 minus 6i. Here's a complex number. What is its conjugate? What? Sorry.
Negative 3.
How come you didn't change that sign? You're not supposed to, right?
That's
The
the
real part
real.
stays the same. Negative 3. What part changes sign?
Imaginary.
The imaginary part. Because now we have to do something with this. Okay? Now we have to be able to do something with this. And here's what we're going to have to do. Are you allowed to have a fraction inside of a fraction?
No.
Are you allowed to have a radical inside of a fraction? No. Not in the denominator anyways. Okay? Are you allowed to have a complex number in the denominator of a fraction? No. Okay? What's the only thing I'm allowed to multiply a number by that it doesn't change its value?
1.
So So we have a choice. We have to choose a wise value of 1 to get rid of the complex number inside of our fraction. And the wise value of 1 is going to have to do with the conjugate. I want to do this problem for you so that you can see why it's the wise value of 1. Okay? Excuse me. If we're multiplying this number by this value of 1, I multiply straight across the numerator, right? So in the numerator, what do I end up with? 1 times 2 minus 3i, which is 2 minus 3i. How would I multiply straight across the denominator? Well, we just did it, so let's do it again.
Okay.
What's 2 times 2?
4.
4. What's 2 times negative 3i?
Negative 6i.
Negative 6i. What's 3i times 2?
6i.
6i. What's 3i times negative 3i?
Negative 9i squared.
Yeah. What happens right here?
0.
That is 0. We needed that. Because what happens right here?
It just
That's negative 1, right? So it becomes 4 minus negative 9, which is really 13. 4 plus 9. So I have 2 plus 3i over 13.
why did it change to the plus?
Because I accidentally wrote a plus. Sorry about that. That's a minus. Thank you for asking.
Yes.
Do I have a complex number in this fraction? Yes. Is it in the denominator? Then it's allowed. Okay? So I have to be able to take a complex number out of the denominator. Why did I choose its conjugate? Tell me that.
Because it's
It would make the zeros and
Or it would zero out.
Yeah, it zeroes out these I values, and this I squared is already becomes a real number of negative 1, so I have no more real parts in the denominator, which is what I needed. Does that make sense?
yes.
Okay. So factoring, okay? There's a lot of different ways we can factor. The most common thing that we can look for to begin with is a GCF, a greatest common factor. If I have 2x minus 8, what's the greatest common factor in those two? 2. So if I factor out a 2, what's left from the first term? X. And if I factor out a 2, what's left in the second term? Good. Greatest common factor. Do I need to do a bunch more examples for you? You got that? Okay. The other kind of things that I can do is called the difference of squares. And what did it look like if it was a difference of squares? Well, first of all, it was a binomial. Okay, it was a binomial. It had a subtraction sign because of difference. And each one of these two numbers right here were squares. Do you remember the pattern when we're factoring the difference of squares? If you don't, I will remind you. You get two binomials. It's the square root of the first one at the beginning of each binomial. It's the square root of the second one at the end of each binomial. And the signs are opposite. Do you remember that? We might have the sum of squares. For example, a squared plus 25. Do you remember the pattern when we factor the sum of squares? Okay, we're done. Right? Remember this one was prime? It cannot be factored. The only divisors are itself and 1. Okay, so sum of squares is super easy because you're done. We could have the difference of cubes. What did the difference of cubes look like? Is it binomial? x cubed, subtract because it's difference, and 27. What's true about each of these two terms? Oh, they're cubes, right? Okay. Do you remember the pattern when we were factoring difference of cubes? If not, can I remind you? No, tell me. Tell me.
It's like the first one.
X minus 3 is the first one because it's the cube root of this and the cube root of this, right? It is. You're right. So this one's a binomial. What's this one? Trinomial. The first term is this one squared. The second term is this times this. And the third term in the trinomial is this one squared. What about the signs for the trinomial? Well, the binomial is always the one that's here. The next one is opposite. The last one, always plus. Guys, my favorite part of this is that some of you are remembering this, and that makes me happy. Yes. Okay? So what's the other thing? What's the other thing we could factor? Difference of squares, sum of squares, difference of cubes, sum of cubes. It's not prime. It's something we can factor. So maybe y cubed plus 125. I'm trying to make these kind of easy. You know that we could have a number in front of the y cubed, right? Just trying to remind you of the pattern. But here, remember what the good part, the good news about the pattern for this one? Well, the way I taught you, it's the same pattern as this one, right? I need a binomial and I need a trinomial. The binomial is the cube root of each one of these with the same sign as our problem. In the trinomial, it's the first term squared, then the first times the second, then the second squared. The pattern is the same as this up here. The first sign is the sign in the problem. The next sign is opposite. The last sign is always plus. Okay? Remember that? And then pretty much, we talked about some other stuff last year in Algebra 2, High School Algebra 2. But the last one we're going to talk about today is just a trinomial. If we have any trinomial, for instance, x squared plus 5x plus 6, do you remember the pattern of what we always did? If this is A, and this is B, and this is C, first we found AC. And that's 6, right? And then we found B, which in this case is 5. What multiplies to be AC and adds to be B? Well, the numbers that multiply to be AC are 1 and 6 and 2 and 3. Which one of these pairs of numbers add to be 5? 2 and 3. So at this point, we recognize that A is 1, and if A is 1, we can do our little shortcut, right? We can go straight to our factors to be x plus 2 and x plus 3. If A is not 1, do you remember what we had to do? Okay, so if we started with x squared plus 5x, we're just pretending for a second that A is not 1. We all know that A is 1. We had to split this middle term into two parts. And these two numbers are what determine the two parts. So we had x squared plus 2x plus 3x plus 6. Do you see how those two equations are equivalent? Then we just looked at the first two terms and figured out what was the greatest common factor that we could get out of the first two terms. What are they both divisible by? An x, right? Well, what's left if I factor out an x? X plus 2. Remember that? Now I just look at the second two terms. What are they both divisible by? A 3. Then I factored out a 3. What's left if I factor out a 3? X plus 2. Now, do these two terms have a common factor? What do they both have? An x plus 2, right? See how this term right here has an x plus 2 and how this term right here has an x plus 2? Factor it out. X plus 2. What's left when I divide this first term by x plus 2? X. What's left when I factor an x plus 2 out of this term? 3. See how I ended up with the same answers? This way is the way we have to do it when a is not 1. This is the way we can do it the little shortcut way if a is 1. Do you remember that? That's pretty much the basis of section 1.4 and 1.5. Okay? So I'm going to leave that as our video for today. Work on some of the homework tonight. If you have any questions, please ask me, and we can definitely do some more talking tomorrow. Okay?